Okay, so we're going to go ahead and work through one more problem from that calculating heat side, and we're going to look at the part 2, and I think it's question number 8. Number 8. I had to go back and make a change because I left a piece of information off of that problem, but it should be fixed by now. So we're going to go ahead and start with that one, or end with that one, and then you guys will be responsible for finishing the other 6 problems or so on that worksheet, okay? All right, so let's see if I can get this to work here. Present. Okay. So we said just a minute ago, whenever the class was in here, that when you're working problems like this one, and if you're looking at that sheet, the calculating heat worksheet, it says number 8, you've got gold that's heated and then it's dropped into water. What you're looking at is, when you have a hot piece of metal that goes into water, it does change the system. Heat will leave one thing and will go into something else. So we know that heat lost would be equal to heat gained somewhere, right? And so that's what we're trying to look at and figure out just missing pieces. So if you take a look at number 8, it says that you have a 125 gram piece of gold that was heated to a temperature of 100 degrees Celsius. So that's where it's going to start, at 100 degrees Celsius, that piece of metal. Now, the specific heat of gold was 0.129. It was dropped into 150 grams of water, whose initial temperature was 25. The specific heat of water is 4.184, and then calculate the final temperature of the system. So they're wanting to know, if you take that hot piece of metal, you drop it into water that's at a certain temperature. After you let it set for a few minutes, what's the final temperature of the system when they're both at equilibrium? When the metal's cooled off and the water's gained some of that heat, what would be the final temperature of the system? Okay, so that's what we're going to look at. So what I told the kids earlier was you really need to make a list with 2 sides, since you know that Q lost, so heat lost is going to be equal to heat gained. And so heat loss means it's exothermic. Heat gained is endothermic. So what we're going to do is set this up. It says that we're going to have our gold side, because we know that the metal is going to be losing heat. When that hot metal gets dropped into water, it's going to lose its heat to the water. So that piece of gold, the mass we said is 125 grams. The temperature, the initial temperature of the system, or of that gold, is about 100 degrees Celsius. We don't know, though, the final temperature. That's what they're asking us to find. What's the final temperature of the whole system? When you put that metal into the water, that becomes one system. So we want to know what's the final temperature of the system. We also have to know, though, our specific heat of gold, which is 0.129. Okay? Now, I'm also going to have my water side. I want to set up my heat side for the water. Okay, I need to know all of the same stuff, the mass, the specific heat, the change in the temperature. So the mass of the water, they tell us here, is 150 grams. They also tell us that the initial temperature of the water, so the TI of the water, was 25 degrees Celsius. We don't know the final temperature of the system. That's what we're looking for. But we do know that the specific heat of water is 4.184. Okay? So having said that, now we're at a point to where we can just start plugging in the 2 sides of the equation. We can substitute in, for Q, the equation to find Q, because you've got all the stuff you need: mass, change in temperature, and specific heat. So let's go ahead and start plugging those numbers in. So I've got my mass of the gold, which is 125, is my M, times my specific heat, which is 0.129, times my change in temperature is going to be TF, minus my TI, which is 100. All right. And we also know, because of the fact that this is going to be our heat lost side, this is going to be negative. We have a negative Q value because we know this is going to be the exothermic side because it's going to be losing heat to the water. So the water, you have 150 times its specific heat, 4.184 times, I'm running out of room. I'm going to go up a hill here. So TF minus 25. Okay? So what I told the kids earlier in first hour was now it just becomes a question of can we do algebra? So let's go ahead and remember how to do an equation like this. I would go ahead and combine like terms. I would multiply the numbers that I can together. So like if I start on the left side of the equation, I'm going to go ahead and multiply 125 times 0.129, and I come up with 16.125. And I'm going to keep that negative sign right there just because I know that this is a negative value. Minus 100, I'm going to bring that down. And then I'm going to do the same thing to the other side. I'm going to multiply my like terms together. So 150 times 4.184. And I've got 627.6 times. I need to bring down the other part of the equation, TF minus 25. Okay. Now at this point, I've got, it's a multiplication or a multiplication, and then you have it times some stuff in parentheses. I told the morning class I don't like necessarily to distribute unless I just have to. So before I start trying to distribute both sides, I'm going to go ahead and just bring over one of those numbers, okay? I'm going to go ahead and just take over let's take over the 16.125. So I'm going to divide both sides by negative 16.125. Okay, and when you do that, negative 16.125, it cancels out on that side, right? So what I'm left with is TF minus 100 is equal to, I'm going to go ahead and do 627.6 divided by negative 16.25. Sorry, 0.125. And I got negative 38.92 times TF minus 25. Okay? So at this point, because of the fact that you have a multiplication problem on the right side, now you do have to distribute. I'm going to go ahead and take that 38.92 and distribute it to everything within the parentheses. So I've got negative 38.92 TF, and then I'm going to multiply 38.92, negative 38.92 times negative 25, which gives me a positive 973. And I'm going to set that equal to TF minus 100. Okay. So at this point, now it just becomes, we've got to get like factors on the same side. Okay. So we're going to take that 38.92 TF and I'm going to move it to the other side. Because this is a plus and minus problem at this point, I've got a negative 38.92, so I'm going to do the opposite and add 38.92 to both sides. Okay, I'm going to have to make some room here. Move it up there. Okay, so I've got 38.92 TF plus 1 TF is going to be about 39.92 TF equals, I'm going to take this 100 right here, and I want to get it on the right side because like terms, right? So I'm going to add 100 over here. So that's going to be equal to 1,073. Now we're almost done. This is a problem now. All you're going to have to do is divide both sides by whatever's attached to that little variable. So 39.92, divide both sides by that. That cancels out. So 1073 divided by 39.92. And I end up with around TF equals 26.87875,752. I'm going to round that down probably to about 3 digits. So I'm going to do 26.9. And 26.9 what? Well, because we're talking about a final temperature, it's 26.9 degrees Celsius. Okay. It's a lot of math. It's a lot of like remembering how to do your algebra 1 and doing the correct order of operations. But the concept, though, is pretty straightforward, right? Heat gained must equal heat lost. You've got to know which side is losing heat, which side is gaining heat, and then set them up and solve them. I hope you do okay with these. Let me know if you have trouble or need some extra help. All right.